So I thank very much to the organizer to invite me, and all of you who stayed here, because this night is a banquet. So what I shall try to show you is that I do have the proposal for the theory which can explain all the open questions of the standard model, and also have the degrees of freedom for scalar fields, for vector gauge fields, for matter, antimatter, for dark matter. And the more I'm working on this with the collaborators, I don't have many, then the most important is Holger Beck-Nielsen, and we meet in this Blade workshop. And the most I am working on is the more answer to the open questions I can provide. So here are some, I hope this will appear on the net. And here it's, you all know this. I should tell this only because I would like to point you out what I really explain. The first few things you all know. So 50 years ago, this standard model made a wonderful next step to the understanding physics of elementary particles and fields, but it postulated everything. It's due to guessing from the experiments, but it postulated everything. Left-handed weak charged particles and right-handed weak chargeless, and then hypercharge was postulated so that electromagnetic charge is there, and you have, as you know, colored triplet and colorless leptons. And I will show you how this I reproduce. And then you have anti-fermions, and then this standard model postulated the existence of the gauge field to all these charges, and these gauge fields are written here. You all know that, and I shall show how I can reproduce this. So handedness is 0, weak charge has only weak bosons, hypercharge is all 0, and colored charge have only gluons, and all are in the adjoint representations with respect to the charges of fermions. And then it's postulated also this scalar field, and it got weak charge plus minus 1/2 and hypercharge minus plus 1/2, and gaining non-zero vacuum expectation values, breaking the weak charge and the hypercharge, and correspondingly breaks mass protection. And then the existence of Yukawa coupling, existence of non-zero vacuum expectation value are already set, and here are Higgs. They are indeed doublets, but only these parts are getting non-zero vacuum expectation value, so that they dress, one of them dress U quarks and neutrinos, and another one dress D quarks and electrons. Now, and there is the gravitational field. Everything is postulated, but it works perfect. So you all know about this, but there are additional phenomena which people are searching for, the dark matter, matter-antimatter symmetry, the dark energy, the observed dimension of space-time, and many other phenomena. And my answer to this today talk should be, I can explain the observed phenomena and all the answers to the standard model, and I haven't come into contradiction with the experiment yet, but of course I could. But so many things are covered that I trust myself. And it is, here it's written, it is obvious the time to go to a next step beyond the standard models. And this is very important. And what questions should one ask to find to the next step? First, where the family members originate, these are U and D quark, where charges originate, where charges of family members originate, of why they are so different, and left and right are so different properties. Where families originate, how many different families exist, why do family members, quarks and lepton manifest so different properties if they start all from massless, which is beautiful, that this assumption. How is the origin of the scalar field connected with the families? How many scalar fields do we have? Why the Higgs scalar or all scalar field, something with almost the charges of, with the fundamental representation, weak charge, how it comes, why it's doublet? And are there additional scalar fields which have charges in the fundamental representation, like color charge? And I will tell you that all this is possible. There are much more questions which I shall not be able to tell. So my statement is an elegant, trustworthy next step should answer many of these questions, not only one. And there exist not yet observed families, gauge vector fields, scalar gauge fields, and dimension of space-time is for sure larger than 4. And in the literature, one cannot really find the families, the explanation for the families. I shall do it. I mean, people take the group and say this should be the group which is a family group. But I will show the nature requires that they are families. There is several groups and there are several unification. One of these, SU5 was discussed, SO10 was mentioned, of Fritsch and Minkowski. Supersymmetric theories have several nice properties. I don't see supersymmetry in my theory. So the spin charge family theory does offer the explanation for all the assumptions of the standard model and making several predictions. And let me briefly make the introduction into this theory. So I shall start with 13 plus 1 dimension. And I shall show to you it's nothing but fermions with 2 kinds of spins and gravity. And all the rest comes out scalars and vectors in 3 plus 1. So there are 2 kinds. This I shall explain in more details. The Dirac one are known for a long time, and the second one describes families, and I shall show you why it describes families. So these 2 are the only Clifford algebra objects which exist. There are no third kind of. You could work in the Grassmann space. I found this in the Grassmann space. But it's, if you don't go to the Clifford algebra, nature certainly prefers Clifford algebra. You would have fermions with a right statistic, but with the wrong spin. Spin would not be in fundamental representation, but you would have triplets. And color of known vector-like representations. All vector and scalar gauge fields origin in gravity, as I said, and there are, to each of these 2 Clifford algebra objects, this is SAB indeed if you multiply with I over 2, and this I call S tilde AB, which generates families, and these are 2 spin connection fields connected with this and these 2 generators of the Lorentz transformations. And there are field binds. And there are all, which is very important, is that if you have this index, space index 0, 1, 2, 3, then you have vectors, gauge vectors, which you know in the ordinary space. If this is S5, 6D, then you have scalar fields, which also are gauge fields of these operators, and they can be determined uniquely with field binds if you have no spinor presence. So I think I shall show you why this spinor present is needed. So spinors interact correspondingly with the field binds and two kinds of spin connections fields, and I can prove you that the appropriate Lagrangian for the gauge fields, which we know come from the gravitational field, but this also other people from the Kaluza-Klein theory know. Some of this I proved, but many things were known before. So there are two kinds of spin connection fields. One behave like doublets, so that are in doublets with respect to weak charge, and another SU2 charge, and this another SU2 is responsible for this hypercharge. And then the other scalar fields, and this explains Higgs scalars and Yukawa couplings, but I have many, not so many, I should tell you how many scalar fields. When the space index is equal to 9, 10 up to D, you have colored triplets. Again, in the fundamental representation, like Higgs fields with respect to the space index, and all the other charges are in adjoint representations. So you have just ordinary physics in 3+1 dimensions. I need condensate. I need condensate to break symmetry. And then I also need non-zero vacuum expectation value. It could be that condensate is something which is well known in the solid state physics, and nature is repeating in the many body problem situation, almost everything in steps. So it's elegant also in this. And then this breaks CP symmetry, couples to all the scalar fields and couples to all the vector gauge fields which do not stay, with which it interact. So we see before the electroweak break only hypercharged vector field massless, weak vector field massless, color, and gravity. And SU2 symmetry breaks due to this condensate, and so that another gauge field become massive. I always put here, sometimes I forget the references where we published. Non-zero vacuum expectation value, I repeat it. I mean, the idea is repeated. It could be that Fritsch is right. It's nothing but like the non-zero vacuum expectation value. This I don't see really, but one should show that it works. So I am not so far that I would say, I just repeated the idea of the standard model in this sense, but all the other is not. And if this is correct, then it goes into the physics beyond, this is after, beyond in 1+3, after electroweak break, as you know. Everything, then it works as it should. All this is not important. I would need much time to explain. I think it's extremely encouraging that I start with very simple starting action. Almost nothing is there. Gravity and fermions of two kind of spin. And when I come down to 3+1 dimension, words start to be colorful and splendid. Now I can also explain, like SO10, which is expected, triangle anomalies miracle, but here it's much better than Peter in SO10 did, because there you have to put by hand connection between spin and charges, and I don't need to. It's just there, so that I think it's better. Now, let me now start with this. So these are two kinds, as I said, of Clifford algebra operators. I found this second one in Grassmann space. One could work as well in Grassmann space all the time with these two kinds, but Holger Beck-Nielsen said, but let us write in a more fashionable way, and so this is changed more or less only the notation, but you can, you need, in the Grassmann space, the vacuum can be trivial. Here you have to discover this vacuum, but it's not difficult. So, but how gamma, Dirac gamma proceed, you know, everybody knows. So if you write down, and I shall show you how U and D quarks can be written in this fashion, if any Clifford algebra object is written in such a way, which can be, then gamma is just multiplied from the left-hand side, while the gamma tilde must jump over, and when it jumps over even, then it multiplies with I. When it jumps over odd number of gammas, like here, then it bring the factor is minus I, and it's all the rest is simple. Everybody can do that. This technique is beautiful. You will see how, at least to me, but I think everything is very simple. So I have then two kinds of the generators of the Lorentz transformation, SAB and S tilde AB, and they, S tilde, define the equivalent representations with respect to SAB. It means they commute. They have all the ordinary commutation relations which you know already. And if gamma A are used to describe spin and all the charges, then I should, if I know, we all know now, that gamma tilde A exists, I either should show that nature uses it, or I should show why it does not manifest in the world where we live or observe. But we do have families, so it does show up. Now this is my simplest. I saw many different Lagrangians. This is my simplest Lagrangian. This is for fermions in d dimensions in the presence of gravity. And here it's the Weil Lagrange density. And here is how covariant derivative looks like. So you have here the generator of the Lorentz transformations in gamma in the with the internal space of expressed with gammas, and the gauge field is here corresponding, and here it's in the internal space of gamma tilde, and here is the gauge field. So then I use the linear. I don't see that a quadratic term is here needed. It could be from something else, but usually if you go to high dimension, you always can come to lower dimension with some additional term. So I think that If this would be needed, I should start with the higher, I mean, the most probably with infinite. And here you have this curvature expressed with field binds and spin connections, and this is usual gravitational approach, nothing new. But everything behaves like it should, so I shall not explain this. It's just the ordinary. If you vary this linear action with respect to this gauge fields of gammas, you will get this expression completely. Oh, what I did. Oh, I should have to go. Yeah. So, which is completely expressible with field binds. You see it here. If there is no fermion present. So if there are fermion present, then you get here additional contribution, and here is where this this condensate start to play a role, and a similar expression you get also for this omega with tilde. Now, fermions. First, let me somehow show you. You always can write down this density Lagrangian as the sum over m. M means 0, 1, 2, 3. S means 7, 8, or 5, 6, and then 9 up to 14. And this will be responsible for matter transitions from matter to antimatter, and this is from the left to the side, left-handed to the right-handed, and giving mass to fermions. Now it's only how this is one expresses. You see all are expressible. These are written in the terms of gauge fields, or are expressible either with omega, and this is the space index. It can be m also, and then you have gauge fields. This you can calculate, and these are spin connection of fields of the S tilde AB. Now you can do this, but I must admit that, of course, nature could go a different way. She could break symmetry differently. Why she did not, this I don't know. I looked at 3 plus 1 and say, she made the decision. And then if you assume the condensate, then you see that it helps. But if she make the decision as she did, then, oh, excuse me, then, no, now I'm always doing something wrong. Back. Aha. So I did too much. So this is how you express with all kinds of these Lorentz transformation, either with tilde or without. And here you see this tau 4, which I call spin quantum number, which defined, I shall show you, this defined together with SU2 of the second kind, the hypercharge, as you see here. Prime is the superposition of these two. This could be 1, and then it's here sum, and here here it's minus plus, and then you can this color electromagnetic charge, and this is like in the standard model. So everything can be expressible in this way. Now this is the way of breaking, and the breaking is important. It's not that it can be any break. If it comes from infinity, one would see that it jumps over 4. It always stays within dimensions which are even but divisible only with 2, not with 4. So it comes from 113 down to SO17, and this is SU6. And then this is important because I can explain to you why weak charge and left-handedness is connected and hypercharges. And then you have here another break. And here you end up with 8, 2 to the 8 over 2 minus 1 families, which then divide into 2 blocks of 4 families. So this is written here, and this I am predicting 2 groups of 4 families. And I need, as I said, appearance of the condensate, and they are of 2 right-handed neutrinos coupled to spin 0, and then it works. Everything works up to. It's not a lot of work behind, but it is a nice, I think, presentation of the explanation of the assumed quantum numbers of the standard model. This is about electroweak breaks. I'm hurrying up. Now, this is what I said. This is only to illustrate in d dimensions any. Everything is boring. Only 2 kinds of spins, gamma and gamma tilde, and gravity. 2 kinds of spin connection, but this does not matter. So when nature looked down, she said, there is so beautiful, so let's come down to 3 plus 1, and then you see whatever we have seen up to now. And we have, because of that, our beautiful. Now I must spend 1 minute for this technique of Holger and me. You can write, you make a choice of Cartan subalgebra, which you always do in any theory. And if you do this in a clever way, you have less work to do. So now you can invent here the superposition of this gamma, and the same for gamma tilde. First of gamma minus plus gamma b, this is nilpotent, so you know square is 0. And here is projector. If you here multiply with the same one, you will get here the same back, whatever it is. So from this object, I can make the whole presentation of my quarks if I, as I said, make a choice of this Cartan subalgebra. So gamma, which one should, it's too difficult now in a short minute, but gamma E transport k to minus k never to k, this is nilpotent, this one is, this is nilpotent, this is projector, and never to k and gamma tilde are opposite, and this is why they form different representations. So Taylor representation in 13 plus 1 includes all quarks and leptons and all anti-quarks and anti-leptons. You're always used to think differently for quarks and anti-quarks, but this is 64 members. Of course, they include spin up and spin down and everything. Now you will see how it looks like. This is one representation which you look from the point of view from the handedness in 3 plus 1 is right-handed. You can use S01 and you will get spin down. And if you use gamma 0, gamma 5, or gamma 0, gamma 7, or gamma 0, gamma 8, you will come down to this left-handed. And you can immediately see that left-handed all have spin up and down. And you see that this right-handed, you just make the analysis, this is weak charge and this is another SU2 charge. Here it's doublet, here it's a doublet for weak charge, and here is singlet for another one. And this I showed you before. This is the, I call fermion charge, which is 1,6 for fermions, minus 1 fixed. This I shall show you. And then the sum of this and this give you this. And the sum of this and this, as you know, give you charge. So this is all like in the standard model, except that it just comes by itself. Now it's one part, the same part, but for the antiparticle, and you will see immediately here left-handed have no weak charge, and the right-handed are weak doublets. So it's by itself. And if you would have here leptons who are chargeless, here it's for leptons, for anti-leptons is minus, 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 10 minutes. Oh, now I have to stop to explain this. You will have there 1/2 instead of minus 1/6. So everything is working, and now I can show you second quantization of fermions. You just put this, what I said, here, the product. This would be U1 right-handed. And here you take the complex Hermitian conjugation. And here is, this is creator, annihilator, and you can make, and you, all of them. And you have here, you have to invent the vacua, which is simple. And then you have this creation annihilation properties on the vacuum. So very simple way of understanding. And then I have gauge fields. Of course, the gauge fields are all expressible. The vector gauge fields which we observe are expressible with omega st, while those which we, and you can show, I prove this, how this can be expressed with the, I mean, this goes down to this ordinary presentation when you proceed to go to 3+1. And also scalar fields exist. This I don't need to invent. Scalar fields are the superposition of filbines of two kinds, these with tilde and those without. And this is those without, and this is with the tilde. And if they have the space index 7, 8, you will see that they are making the these doublets of Higgses, while these with 9 up to 14 will make triplets and anti-triplets, and this will transform positrons into quarks and anti-quarks into quarks, making transition between anti-particles into particles and back. And if I would not have this condensate and the expanding universe, this would just stay, but then this goes in a right direction. So this is this condensate. I shall not spend time now, only if you ask me. And here it's doublet. So only this part of the doublet, it's in the Higgs, getting non-zero vacuum expectation values, while this one does not get non-zero vacuum expectation value. But indeed, they are doublets. You see with respect to weak charge, and they have the same. I mean, for this and this have to be just like you are. These are all scalar fields which occur, and this occurs for the lower 4 families. These are quantum numbers. These are for lower 4 families, and these are quantum numbers, and these are for higher 4 families. And the higher, this is how this everything can be expressed. This is the mass term, and you see I calculated quantum numbers for this, which got non-zero vacuum expectation value. So there are all these non-space indices have the adjoint group in the adjoint. They are in the adjoint representation with respect to these groups, and while these with respect to the spin index, they are space index, they are either triplets or singlets. These are how families, two groups of families, and now I can create the mass matrix. I don't know what the numbers are, but what I do know is what is the symmetry. And now I could feed this to experimental data. Now I have to hurry up really. And if you know, any 3 times 3 mass matrix, submatrix of 4 times 4 mass matrix is uniquely determining, because if it's unitary, the 4 times 4 mass matrix. So if the experimentalist will give me with all the digits 3 times 3 mixing matrix, I would tell this is 4th mixing matrix, and I can tell you what is the mass, even if the mass of the 3 first families are not accurate enough. But this is not possible. So this is... Yes, you can make. I mean, I can see our fields. I shall leave here how these gauge fields, scalar fields. It's not only scalar, which is Higgs kind. This is another scalar, which is triplet and anti-triplet. And you can see here the diagrams how can be eaten, or one can give, and another one is eaten, and then from positron and anti-particle you get quarks. Anti-quark you get quarks, and the same is, yeah. Yeah, no, this I did. Yeah, this I am 100%. It's open to. No, it's only to have the feeling.
So, are there questions or comments?
Thank you.
No, it seems that your theory is very ambitious, no? Because this
Yes.
spin charge family, from this you want to derive basically all the laws of nature.
Everything. Yes.
Yeah. I did not understand very well what is the status of the scalars in your theory. At some point you mentioned that all scalars have zero mass.
At some point they
Yeah.
are gravitational and have at the beginning zero mass all over.
But at some point you have to get, of course, the Higgs scalar, and you want to get the Higgs potential. You want to get electroweak symmetry breaking, and you will probably get also some electroweak vacuum energy. And the question is whether you, in your theory, you can do that, and moreover, whether you can cure the or the cosmological constant problem, or if you can say something about it.
Yeah, I know more, but I derived from the gravitational field this I proved, that I can get out this Lagrangian for the gauge fields in 3+1, and also for the scalars. And before condensate, everything is massless. Condensate makes some through the interaction. I mean, it interacts with some fields and not with the others. So if I know how and why condensates occur, this I must admit no. I assume that it occurs, and then if it does, then it has the correct properties that you see below this condensate, because below this scale, which should be at some 10 to the 16 or higher. This I don't know. It should be of this kind.
But does your theory give some guidance on how to construct the Higgs potential, where it comes from?
It a scalar potential. Scalar potential should come from gravity. Everything comes. Like this one which I showed you for vector gauge fields, also the scalar gauge fields came from field binds and spin connections of two kinds.
It is nice to know that you try to derive the Higgs potential from gravity. I also did this in a paper that I published last year, actually, not from your framework, but from Browns-Dicke theory, and it is
From
good.
gravity?
Yes, from Browns-Dicke.
But I did this much. This I'm working on many years already. I mean,
We can discuss. Don't worry.
I found in 92.
Okay. Thank you very much.